me check something. So how's the microphone quality now? Can you hear that okay? Okay. Let me know if more problems come up. Okay, so I'm doing this exercise on Desmos. You can do it any way you like with a graphing calculator or with other software. But let me take a minute and ask, did anybody get... Oh, people got kicked out. Yeah, sorry, some of y'all got kicked out. I'll try to be quicker about getting you back in. So we're doing this problem written on the board. And I've done it on Desmos. You can do it on Desmos or graphing calculator, whatever you like. Did anybody find an average rate of change on the interval 1 to 1.5? Just you'd like to volunteer, send me a message or put in the group chat. Or just yell it out. So in that case, I'll just share what I've got. So here's the graph of the y equals square root of x. And to calculate the average rate of change from 1.5, or from 1 to 1.5, so like 1 to 1.5, on that interval, I want to take the change in y over the change in x. So that's going to be the square root of 1.5 minus the square root of 1 divided by 1.5 minus 1, which is just 0.5. Calculate that out to 0.4494, so on and so forth. Calculating that average rate of change from 1 to 1.1, I have to take change in y value divided by change in x value. So change in y value, root 1.1 minus root 1 divided by 0.1, giving me 0.488. So that would be the slope of the secant line going from 1 to 1.1. Finally, that average rate of change from 1.01, from 1 to 1.01, I have to take difference in y values, that's root 1.01 minus 1 divided by 0.01. Here I'm getting 0.498756, and so on. So would anybody like to volunteer? What do you now expect is going to be the instantaneous rate of change at the point x equals 1? So that is to say, what do these numbers look like they appear to be converging to?
I mean, 0.5.
Yeah, that seems reasonable to me. So the instantaneous rate of change at the point x equals 1 is going to be the limit of the average rates of change as the right-hand endpoint gets closer and closer to 1. And in order to check that out, what I can do is I can draw the line that goes through the point x equals 1, y equals 1, and has slope 1/2. So what's that like slope, point slope form, right? Like y minus 1 equals the slope times x minus 1. So the slope of this line is the instantaneous rate of change. And it's what we call a tangent line. It lies tangent to the curve at x equals 1. So it does appear that 0.5 was the correct slope. I can also try to draw some of those secant lines. Like if I want the secant line that went from 1, 1 to 1.5 and then square root 1.5. Like I'll draw both the points. So first here's 1, 1. I don't know, it didn't draw it. What's the problem? 1, 1. And 1.5 square root 1.5. Okay, there they are. And the slope of the line between them was this, right? I just copy and paste that. So if I want the line, that goes through 1, 1 and has that slope, It's pretty close to the tangent line. Let me show the tangent line there. It's pretty close to the tangent line. So the green line is the secant line between the two red points, and you can see how the green line actually really does intersect those 2 points. And the black line is the limit of the green lines as that other red point slides closer and closer to the fixed point 1, 1. I'll give you some more demonstrations later on, but here I'm really interested in computing average rates of change, estimating instantaneous rates of change. It's a little reinforcement from last time. So are there any questions or comments on that?
No.
Okay, cool. So let's talk about limits. So I'm going to introduce some notation to you. And let's do mic check again. So can you all hear me just the same, just fine?
Yeah.
Okay, good. Thank you. So we can talk about like a function having a limit. So let's start with some function y equals f of x. And we can say that the limit, we write lim for limit. So you can say the limit as x like approaches a number a of f of x. So this is going to be a definition. This is like section 2.2 of the book if you want to follow along or study along. We say the limit of a function f of x as x goes to a is equal to L. This means intuitively that whenever x is very close to a, f of x is very close to L. So it means whenever x is very close to a, f of x is close to L. And you might reasonably ask, like, what does it mean when you say close? And there is a more precise definition of it. There is a more precise definition of a limit. I can show that to you. And maybe I will. But first, let's sort of like give some example or get some intuition. Like if you go back and look at f of x equals square root of x, and you say something like x equals 2, and I can ask you, what's the limit as x approaches 2 of square root of x, right? So I'm saying, like here, a is equal to 2, limit as x goes to a, its limit as x goes to 2. Here, f of x is square root of x. I can ask myself, what's the limit as x approaches 2 of f of x? And so how can I read this off, like from the graph? You're thinking that, like, okay, so let's look at values of x that are close to 2. And I'll put those in yellow. Right? So these are values of x that are close to 2. You don't even need to consider like x equals 2, just the things that are close to 2, but maybe not equal. And what are the corresponding y values? So if I trace out this point of the graph, it's over there. And when x is equal to 2, then y is equal to the square root of 2. And so now you're looking at this and you're just saying, well, you're telling me like a very common sense thing that like as these x values get closer and closer to 2, then the y values are certainly getting closer and closer to the square root of 2. And so that's all this concept of limit is saying, which might make you say, like, why do we care about it at all? Like if you draw this graph, that's obviously what we're going to learn is continuous. Like you can draw the graph without picking up your pencil. There's no breaks. There's no issues. Of course, as x gets closer to 2, the y values will get closer to the square root of 2. There's no problem. But we're really interested in limits because we want to compute average rates of change. So perhaps what's going to be more interesting for me is to look at one of these formulas for the average rate of change and then compute a limit that way. So for instance, say that I want the average rate of change of this function y equals square root of x. Let's just work with square root of x for the moment. Say I want the average rate of change on this interval from 1 to x. And I'll give you a moment. So take like 15 or 20 seconds. Please write down the formula for the average rate of change of the square root of x on the interval from 1 to variable x. Give you a minute to work through that. And you can type any question. So after giving you a minute to write down the definition of average rate of change, I'll also write it down. I'm going to call it g of x. That'll be a new function I'm defining. So the average rate of change of square root of x on this interval is going to be square root of x minus square root of 1. Square root of 1 equals 1 divided by x minus 1. And that's definitely what we were calculating previously, right? So when we had x equals 1.5, we had root 1.5 minus 1 over 1.5 minus 1 equals 0.5. On the interval from 1 to 1.01, we had square roots of 1.01 minus 1 divided by 0.01. So this definitely matches what we were computing before when we were finding the average rate of change. And you remember that we said that this average rate of change appeared to be approaching 1/2 as x approached 1. So to put what we said in this new language, what we were saying at the top of class is that it appears like the limit as x approaches 1 of g of x is equal to 0.5 or 1/2. Let me pause to answer questions. So why is it that formula, and why is it 1/2? So it's that formula because remember, average rate of change from a point to another point is the slope of the line between them. So average rate of change is that slope delta y over delta x. And so the change in the y values is going to be like y2 minus y1 over x2 minus x1. So if average rate of change on 1 to x, the 2 points that you're using to make your secant line are going to be 1 and square root of 1, and it's going to be 1 and square root of x. And therefore, the change in y values, the y2 minus y1, is going to be root x minus 1. And the change in x values, x2 minus x1 in this case, is going to be, oh, excuse me, this is x. You plug in x, and you get square root of x as the answer. So the change in x values, x2 minus x1, is going to be x minus 1. So that's the definition of average rate of change on an interval. And so why is it approaching 1/2? So that goes back to the exercise at the beginning of class. Let me share the screen to Desmos again. So remember, we calculated the average rate of change on the interval from 1 to 1.5, and we saw that it was 0.449. We calculated the average rate of change on the interval from 1 to 1.1 and saw that it was 0.488. We calculated that average rate of change from 1 to 1.01, finding the answer to be 0.4987. And from this, we conclude that it appears that the average rates of change are approaching 1/2 as x approaches 1, right? Because as this x is getting closer and closer to 1, you know, x was 1.5, x was 1.1, then x was 1.01. As x got closer and closer and closer to 1, those average rates of change, so g of x is the function that gives us the average rates of change, those average rates of change got closer and closer to 1/2. And when you've got a situation where x getting close to a number means f of x gets close to another number, that's when you say the limit of the function equals 1/2 as x gets closer to 1. And I'll pause for more questions and clarifications. Okay. So that's why we like limits, because they help us talk about these average rates of change. And so the instantaneous rate of change being 1/2 that we figured out That was like the limit as x goes to 1 of g of x. Another way to see this, we can do this graphically. Let's go back to Desmos. So let's go back to our function g of x equals square root of x minus 1 divided by x minus 1. This represents the average rate of change on the interval 1 to x, but even if we didn't know that, we still have this function, right? And you'll notice that if you try to just plug in the number 1, you'll have a bad time. What's that guy from South Park that always tells you you'll have a bad time? You'll have a bad time because you'll plug in the number 1, and then in the numerator you'll get 0, but in the denominator you also get 0. And we can't divide by 0, so that doesn't really help us. But what we can do is we can ask, what do those values of g of x approach as x approaches 1? In order to do that, we can look at this graph. So here's the graph of g of x. And you can see what's happening as x gets closer to 1. We can zoom in on it there. So here's x equals 1, and the graphing software doesn't identify that there's doesn't identify the issue of division by 0. It just sort of draws the line straight through. So when x is equal to 1, g of x is equal to this value. And okay, yeah, there it is. So it says undefined because you can't divide by 0. But what's the limit of g of x as x approaches 1? Well, you can see what's this number? Well, here's 0.4, and here's 0.6, and this number right in the middle is 0.5. So you can see as my x values are sliding towards 1, my y values are sliding towards 1/2. And you can see as my x values starting bigger than 1, but heading towards 1, get closer and closer, the y values are still getting closer and closer to 1/2. But they never actually get there because when you're literally equal to 1, the function is undefined. So that's why we have to use this concept of a limit. We're saying that the limit of g of x is equal to 1/2 as x approaches 1, even though g of x is not defined at the point x equals 1. So that's why limits exist. That's why we have to talk that way. Okay. What I want to show you next is actually another example. Yeah, okay. Do you mind if I answer this question for the whole class? Getting a private question. Okay. Yeah, so I'm getting a private message question, like what if, like we had talked about instantaneous rate of change at x equals 1, and the question is, what about if like you used a different value of x, like you used x equals 1.5 or x equals 2, would you get a different value for the instantaneous rate of change? Would you get a different value for the limit? And the answer is yes. And let's try to calculate that. So I think, like, what if we used x equals 2? So you looked at like the average rate of change of the function square root of x from the interval from x to 2, or maybe from 2 to x. You know, depending on whether you want to think of like x as bigger than or less than 2. So what if you did that? And I'll redraw the function. So we're thinking of square root of x again. We're thinking of instantaneous rate of change here at 2, and we're thinking of taking values of x, you know, either to the right or to the left of 2. I'll just draw one to the right of 2, but thinking of taking values of x that are close to 2, and then calculating the average rate of change on this interval. That is to say, calculating the slope of the secant line. And then asking yourself, is there a limit of those numbers as x gets closer and closer to 2? And so first of all, we would need to look up for ourselves, like what's actually the average rate of change? It's the change in y values, delta y over delta x. So y equals f of x equals square root of x. So if I take something like f of x minus f of 2 divided by x minus 2, for instance, so that this like matches with the picture that I've got, like the slope of this secant line would be the change in y values, the square root of x minus root 2 divided by x minus 2. And so for any, and this is like your new g of x. So for any x, you can calculate. So x could be like a variable that moves around, but it's close to 2. So for any x, you can now calculate the average rate of change from 2 to x. It's given by this formula, root x minus root 2 over x minus 2. And now the limit, now the instantaneous rate of change at x equals 2 is going to be the limit as x approaches 2 of g of x. And so g of x, once again, it's not defined when x is equal to 2. We couldn't just plug in x equals 2 because of the division by 0, but what we can do is we could say, we could draw a graph, or we could make a table of values. We could ask ourselves, is this function approaching a single number as x approaches 2? And one way that's kind of nice to figure this out is, well, you all know by now that I kind of like Desmos for these demonstrations. So let's figure it out. On Desmos, so I can use my new g of x representing the average rate of change, which we just wrote down was like square root of x minus square root of 2 quantity divided by x minus 2. And we were interested in like what happens as x gets close to 2. So like the limit as x gets close to 2. So zooming out, so here's x equals 2, and so what, and definitely if I plug in 2, it's undefined. But if I look at values close to 2, what are we approaching? Like it's staying close to 3.5? 3.539. It's probably an irrational number, but it's close to 3.5. Maybe 3.53. So this limit is maybe approaching, what are we seeing, like 0.353 as we're getting close to 2. So I think there definitely is a real number that is the limit as x goes to 2. So those average rates of change are approaching an answer that's approximated by 0.35. If we wanted to find the exact answer, we'd probably need to do a little bit of work for how to calculate this limit algebraically. And we'll learn about that probably in the next lesson. Okay, so any further questions about that? So that's this concept of limit. The official intuitive definition is limit as x approaches a of f of x. So you start with some function f of x. You start with some point a. The limit as x gets close to a of f of x is equal to L if it's true that whenever x is close to a, f of x is close to L. And if you want to try to make that more precise, you can say like, well, I guess this means something like whenever the absolute value of x minus a is close to 0, the absolute value of f of x minus L is close to 0. So this is an equivalent definition that's like a little bit more technical. X being close to a should be the same thing as the absolute value, like distance from x to a being close to 0. F of x being close to L should mean that the distance from f of x to L, that is to say, absolute value of their difference, is close to 0. If you want to be like really formal, you would say something like for any number, I don't know, call it e, for any positive number e, there exists another small number, I don't know, call it d, such that whenever distance from x to a is less than d, then distance from f of x to L is less than e. That's a formal definition of a limit that you don't need in order to pass this class, but you'll see in an analysis class if you go further on in mathematics. But here now in Math 210, I really want to focus on the core idea, the core philosophy of what does a limit intuitively mean. Intuitively, it means that as x is getting close to a fixed number a, in this case a is equal to 2, your y values are getting really close to L. In this case, L is roughly 0.353. Okay. The next example I want to show you. Let's take y equals f of x, and let's take f of x equals sine x divided by x. And so what I want you all to do is take a few minutes. Can you find the limit as x goes to 0 of sine x over x? So you're not going to be able to do this just by looking at it. You're not going to be able to do this with algebra. But what you can do is you could graph it. You could plug in sine x over x into Desmos. Ask yourself, does it appear like these values of sine x over x are approaching a certain number as x approaches 0? Another way you can do this is you could make a table of values like for x and for sine x over x. You'd need like a graphing calculator for this, but you could pick something like 0.5, 0.1, 0.01, and like even like 0.001. What happens when you plug in these numbers into sine x over x? Does it appear to be approaching a singular number? So graph it or fill in the table. Either way, take a minute or two. Can you find out what do you think is probably going to be the limit as x goes to 0 of sine x over x? Give you another moment or two to work. Be welcome to chat me your answers when you have them. Yeah, I'm getting some answers in. Thank you. I'm going to try to show like a couple different perspectives on this. So one perspective is like the unit circle perspective. And in this case, you often call x by theta. So like, I mean, you could still call it x, but so in the first class period, we remarked that I kind of said it offhand. I didn't spend a lot of time on it, but a radian angle theta is really a measure of how far along the circle you've gone. So for on the unit circle, angle theta is this length, because if theta equals 2 pi, then you're all around the entire circumference. And sine theta, you might remember, is the y value, because this point is x equals cosine theta, y equals sine theta. And I could have said x, like this would be x, and cosine x, sine x over x. It's just, people often call the angle theta. So what is sine theta over theta? I'll put sine theta in yellow, that's this line, and I'll put theta in white, that's this arc. So it looks like theta is a little bit bigger than sine theta, but you have to imagine, as this angle squeezes down to 0, what's going to happen to the ratio of these lengths? Like if you drew a much smaller angle like that, then you would compare this to that straight line. And it looks like those lengths are getting closer and closer together. In fact, it looks like this limit, as theta goes to 0, is equal to 1. That's like the trigonometry perspective. There's also a, and I'll just share this like ever so briefly. You can also just graph it. You can just graph sine x over x, and you can see that it's not going to be defined at x equals 0. And yet, you can also see that as x approaches 0, those y values are approaching 1. Whether you go from the left or the right. So here I am coming into the right, and x values are approaching 0. Those y values are approaching 1. So there's two different ways to see it. One graphically, one with the trig business, and you could have also filled in the table, and you would see those numbers sort of creeping up to 1. So what we learned is that limit as x approaches 0 of sine x over x is equal to 1, because as those x values get close to 0, those y values get close to 1. And that's something we will use. Just one more quick thing, like if you graph sine x, it kind of looks like this, right? So where this is pi over 2, and that with minus pi over 2. So sine x over x is like the average rate of change from 0, 0 to x. And so the fact that I wrote L, but limit as x goes to 0, sine x over x is equal to 1. So this quantity is like the average rate of change from 0, 0 to x sine x. And since we figured out this limit, that's telling us the instantaneous rate of change is equal to 1. And therefore, if you look at the line through the point 0, 0, and with slope equal to 1, like that, it's sort of showing you that this tangent line to sine of x is just a straight line y equals x. We'll learn more about that in subsequent classes. Okay, learning objectives for today. What is a limit? Reinforcing average rate of change, and calculating limit sine x over x. So thank you, everybody. Have a great day. Sorry for going 2 minutes over. Happy Valentine's Day. I'll see you on Monday.
See you Monday.
See you.
Bye.
Take care.
Thank you.
Thank you. Have a good day.